Yes, ma'am, we have enough participation. We can start now. I am there with the introduction. Yes, so good evening and welcome to all. We, on behalf of Technology Robotics Society, in association with IEEE and Center of Excellence in Artificial Intelligence, IIT Kharagpur, feel immensely honored to invite Dr. Sinnu Thomas as our speaker at the guest lecture series as a part of Winter School going on. Dr. Thomas is currently working as an assistant professor at IIIT MK. She has also worked as a postdoctoral research associate with the Department of Electrical Engineering, KU Leuven, Belgium, in collaboration with Ford Innovation and Research Center, Germany, and the USA. She was awarded the Gandhian Young Technological Innovation Award and the Best Thesis Award at CICT 2018. She was also nominated for the Ranjan Memorial Award 2018 by IIT Kanpur and was the finalist for Falling Wall Labs, Leuven, Belgium. Recently, Dr. Thomas has received her COVID-19 research grant. Her research interests are focused on Bayesian optimization for industrial applications, computer vision, and multimedia signal processing. Now we hand over the session to Dr. Sinnu Thomas. Over to you, ma'am.
Thank you, Tanmay, for your kind introduction. And I feel very overwhelmed to be a part of this winter school. And thank you for giving the invitation. And please, as the participants are from the first year and the second year, you are very well invited to halt me or ask me questions anytime. So I'll try my best to finish off by 7:30. We started at 6:37. So I'll try my best to finish off at by 7:30, and I will be covering actually one part of my research, which I recently did on the Bayesian optimization, or you can call it as the Gaussian processes for machine learning. So that work, what I did, and with the current state of the art, what is going on, and I will try to build up the basics of the participants in that area. So coming to the Bayesian optimization. We all know what's human learning, okay? We all know if a child is taught 5 into 3 is equal to 15, 7 into 8 is equal to 7 8s are 56, he knows what will be 9 3s are, okay? So same thing is being applied to the machines also, right? We all know about what's happening in the machine. So machines have some data, you have some data, you try to train that data, you fit in some model on that data, and then based on your inferences, okay, you try to find out, you try to predict what is happening, what is you try to predict the result maybe in the future, what is happening, or you try to predict something out of this data. So that is what is your machine learning in a simple terminology. Now, how is this machine learning actually taking place? Okay, in a computers, how is basically this taking place? In two ways, basically, you can do your machine learning. Fine. So one is your optimization approach. Other is your probabilistic modeling approach. Okay, so I've taken the simple examples in this case, optimization approach and the probabilistic modeling approach. I'll try to simplify as much as I can. And let me tell you, let me ask one thing, Tanmay, is the participants are, since this is more of a machine learning, mathematics will be there. So are you comfortable with the mathematics, or should I skip the mathematics?
Ma'am, we know basic mathematics course. We have completed the first semester, so we would be okay with any sort of mathematics.
Okay. So, okay. Now, the machine learning approaches, basically, if you classify the machine learning approaches, it is basically classified into two, optimization and the probabilistic modeling. So, under optimization approach, what we do is, see here, what we in the previous problem, like in the machine learning, that previous diagram, we said that some learning is taking place. So in the optimization approach, what we do is we try to formulate the learning problem to an optimization problem. Okay, and then you have some cost function. Okay, you have some, like I'll try to simplify since you are all first year students. So cost function is like, what is the cost of you people, like what is the cost that you are attending this program? Okay, the cost of you may be at home. I suppose first years are at home, so you are avoiding all other functions and you are you are attending this program just to get the knowledge. So what is the cost involved in finding out to get something, to get to a problem or to achieve a solution from that problem? So if you have an optimization, if you formulate the learning problem as an optimization problem, what you do is you try to minimize this cost. So that is what is there in the optimization approach. And then you characterize, out of this minimization, there are two types of there are two types of minimas you can get. You can get global minimas, you can get local minimas. Okay, so out of that, which one should I take? What is the characteristic of the best result? What is, what should be my resulting solution? So that is being covered under the optimization approach. Coming to the probabilistic modeling approach, I suppose all of you have done the probabilistic theory in the first year. So the learning problem here is being formulated as a probabilistic model. So the model, what we saw in the last picture, is basically a probabilistic model. So when we talk about the probabilistic model, we know that it's more or less about the uncertainty. Okay. So now when you're talking about the probabilistic model, obviously the probabilistic distributions will come into picture. Fine. Now, if probabilistic distributions like your uniform, Gaussian distribution and all those things, okay, so when distributions are there, obviously the parameters are also there. Fine. The parameters of, suppose, a simple, the normal, the distribution which is there, which you use regularly, is your normal distribution. Fine. So you use the parameters for the Gaussian distribution is your mu and sigma, right? The mean and the variance, right? So you treat those parameters with these probabilistic distribution. And then what you do is, according to the data what you have, you use approximations to find out these, these parameters, and then you say that, yeah, okay, this is the result. So any questions still here? Okay. Coming to the optimization approach, I'll take a simple example. Suppose you have an equation y is equal to mx plus c. You have a linear equation. Okay, you have a linear equation. So here, if I try to plot this, if I try to plot between y and x, I have something, this is my c, and this is what my m is. Okay, I can plot different y's and with different values of y and different values of x. I can have different m and different c. Fine. So in an optimization approach, given these two values of x and y, okay, what will be my c and m? So this m and c becomes my parameters when I consider this equation y equal to mx plus c. Fine. So my job will be to minimize some equation, minimize a cost function in such a way that I find out this m and c. Okay. So I can have c. I can if I have these 2 points and if I want to fit a line between these 2 points. Okay. So this is the easiest way of fitting a line in these 2 points, between these 2 points. Okay, suppose if I have a third point somewhere here, how am I going to fit a line, using these 3 points? I can have, this one solution. So similarly, I can have this solution. Multiple solutions can be there. So that is why I said about the characteristics of the resulting solution. Okay. So my cost function will determine which 2 points I should take so that I get a minimum cost function. Fine. So yeah, so these are different this different type of lines what I get out of all the 3 different points. So how I am going to find out which is my best m, which is my best c. Fine. I'll pose this y is equal to mx plus c as a cost function. See how yj. Since I suppose if I have n number of points, okay, so yj minus mxj minus c, and if I take the square of that, this is basically this function, okay, is called as your cost function, or you can call this as an error function. So if you try to minimize this error function, ultimately what should happen? Your y should be equal to mx plus c. So you have to minimize the difference between y and difference between y and mx plus c. So that is what we are doing it. Fine. So when we try to minimize this function, error function, and attain a value of m and c, fine, that is what is basically your optimization approach, and you can call that as your regression problem also. Okay, so the optimal value what we get out of this error function is the c star and your m star. You do the calculations and you get this m star and c star. Just to have a brief like I'll just give you a hint how to find out this. What you do is you try to differentiate this and put it to 0. So that is what you you make the gradient 0. So that point will give you the minimum error point. Fine. So minimization of your cost function is basically you are learning. If you have multiple m and c, so you go on finding out m and c till you attain a minimum error function. And this problem, this yj minus mxj minus c whole square, this is also called as the sum of square error, SSE problem. Okay, so this is the basic of regression problem or the learning problem in the machine. This is basically the form of a cost function in your regression or the learning problem. So now I said about the zero gradient. Okay, gradient is you're trying to differentiate it with respect to m and with respect to your c. Now, if I want to plot the gradient, fine, you have different methods. You have your conjugate gradient, you have your coordinate descent method, stochastic gradient method. So many, gradient methods are there which can help you to achieve these optimal m and c values. So what you do is, suppose in coordinate descent, what you have is you plot a curve between your m and your c. So it will try to minimize the points in both the direction, in the c direction also as well as in the m direction also. And suppose if I plot the contours for those values m and c, it will be something like this. It will be a circle. It will be a concentric rings. Okay. So I start at some initial point, and then these are basically it's basically a algorithm where you start at some initial point, you start at some m and c, and you try to you just start your optimization from that point. You take the gradient and see whether it approaches 0. If it doesn't approach 0, you take a further step. So this is that step. You take another step and find out a gradient at that point. If you don't achieve 0, you take another step and you move forward till it goes and reaches to 0 point. So this point, so you started somewhere at this point of M and C, and you just go on till you get till you achieve your M and minimum point, minimum error function, and this will be your optimal M and C. And this is an iterative process. So you start at iteration number 1 here, and you end up at iteration number 30, where you attain a optimal M and C. So this is an example of a coordinate descent, and which is an example, which is one of the algo in optimization problems. Coming to the probabilistic, modeling approach. Basically, you have two types of.
Ma'am, Akshat has a doubt. He's asking in the previous slide. What?
Just a second. This one?
No, ma'am. The slide before that.
Okay.
No, the slide before that. Sorry.
Just a second. This one.
Yeah. In this one, Akshat is asking how we are getting the formula for M star and what it stands for.
Okay. M star is actually your optimal value of M when your gradient is 0. Okay. These are the minimum points. Like when your error is 0, you get these optimal values C, and it is just use partial differentiation with respect to, just you do the partial differentiation of this EMC with respect to M, and with respect to C, you will come and hit these values. Am I clear, Akshit?
Yes, ma'am, I think.
Is it okay? Shall I proceed further?
Yeah, sure, ma'am.
Am I going, fast?
No, ma'am, my speed is all right.
Okay, so this is your coordinate. Okay, so coming to now the probabilistic modeling approach, which we will be discussing, in more detail for the Gaussian processes actually. Now, I told you that probabilistic modeling approach, it is more of, the uncertainty. We talk about uncertainty in the probabilistic modeling approach. Okay, so we know that we know the godfather is Bayes and all those things. Okay, so in probabilistic approach, what we say is that you have this linear equation. Okay, y of which is a function of xj is equal to nxj plus c. Fine, and you are adding an alpha term here, which epsilon term here. This epsilon is basically since this is an uncertainty, okay, we are assuming that uncertainty is being characterized by a Gaussian distribution. Okay, Gaussian distribution having mean 0 and variance sigma square. Okay, so you have your Gaussian, you have a noise also which is being taken into consideration when you are talking about the probabilistic modeling approach. So instead of writing like now you have, your Gaussian, linear equation like this. It's an equation of a line like this. So you can put it in the terms of, in the normal distribution. You can write it as normal distribution, where you can say that your yj can be characterized as a normal distribution with mean mxj plus c, and variance is your sigma square. Now, you all might have heard about the conditional probability and all. Okay, so you have to find out the conditional probability yj given your m, c and sigma square. All right, that is what we have to find out. We have to find out yj given your m, c and sigma square. So same thing, I can just put it in terms of the normal distribution. When the normal distribution of with mean yj given mx plus c and your variance sigma square will be the conditional probability of y given all these, your parameters m and c, and now I can take sigma square also. So I can write the p of y given these values as the normal distribution. Fine, since you have this epsilon as the normal distribution. Now, suppose if my x is being distributed as IID, independent and identical samples. Okay, I can write these values. Now my X is being distributed as IID samples, as I have n IID samples. So what I can write is, I can write this conditional distribution, okay, conditional probability, as the product of these normal density. If it is an IID, okay, if it is an IID sample, if my XJ is an IID sample, okay, I can write this as a product of all these normal distribution. And since this is normal distribution, Gaussian distribution, normal distribution, we can write it in this form. Okay, right? So I just, you have your, what is that, 1/2 sigma square and all those things. So I'll just put a proportionality sign. Now, if you look here, this expression, in this expression, yj minus mxj minus c, this is your, again, E of mc. Fine? This is your E of mc. So what we are doing is, and this is your exponential of this parameter. So exponential of E of mc. Fine? And here you have your probability. So if I want to convert it into log, okay, so that becomes your minus log, and this side, on the right hand side, I have this error function. Fine. So what I'm doing is, if I want to minimize this error function, I have to maximize my log, this part, LHS. Okay. So this is my likelihood parameter. I'll come to the likelihood and all those things. So if I maximize this parameter, because this is, minus log, okay, and if I have to minimize this, I have to maximize this, because you have a negative here, okay. So if I have to minimize the error function, I have to maximize this likelihood function. So, this is basically a principle of Gaussian log likelihood, where you can use the, maximization of the likelihood to find out the minimum of the error function. Okay, so now, as I was talking about, this likelihood, and we all know what is Bayes theorem. So your posterior is equal to your likelihood into prior and divided by the evidence. So now, if I put it in terms of the parameters of my line, M and C. M and C is where I, represent my M and C with W. Okay, so I can say that this is my posterior value and this is my likelihood. See, was my likelihood, right? So this is my likelihood, and this is my prior information on M and C, right? So what we discussed in same as we discussed in that coordinate descent. You consider some prior data, you assume from some initial point, and then you just go on decreasing it. So this is my prior information, and this is your marginal likelihood. You can call it as marginal likelihood. Some people call it as scaling factor or evidence. Okay, so where you can write this as why you can write this marginal likelihood as this if you integrate this over for all the values of M and C, you will get this marginal likelihood. So yeah, so this is your Bayesian inference, just to give you a recap of what you have learned in the Bayes theorem. Okay, so now in this case, what we were assuming is, that if you look at this equation, we were assuming that, M is a linear function of, Y is a linear function of xj. Now, in case Y is not a linear function of xj, okay, Y may have non-linear relationship with X. Previously, when Y was having a linear relationship with X, you call it as linear regression. Otherwise, you call it as non-linear regression. Okay, so when Y does not have a linear relationship with X, you call it as the non-linear regression. And the solution to this problem, we have seen the solution for the previous linear regression. The solution for the non-linear regression is basically you create a feature space phi x, okay, which is a function of x, and you represent your Y in terms of these basis function, or the basis function in the feature space. Okay, so now what you will do is, see, suppose this is your basis function. Phi is your basis function in the feature space. Okay, you have your feature space, and you try to this is your W. Your constants, or maybe you can assume it as this is different W from your. I should have written the notation different. This is different W from your previous M and C, which is the parameters. Okay, this is just I've taken it as a constant. So if I represent my function in this form, okay, as a combination of the nonlinear function, that becomes a nonlinear regression. And examples of these WIs can be anything. It can be, one example what I've taken is, this quadratic basis function. So it can be this basis function. When I consider WI to be 1, I can put it as a straight line. When you have a constant line, when you have W2 is, maybe I can take a constant here. So that becomes a straight line. W3 is maybe, that becomes a parabola. And all three, it becomes a quadratic basis function. So I can represent my the X as, in the form of basis function. And then what I do is I try to reduce this fx. Fine. So one of the example of this basis function is basically your Gaussian basis function. This is a common basis function which you use in machine learning. Radial basis function or Gaussian basis function. Exponential of minus x minus mu I whole square by 2 sigma square. Okay. Is it fine? Any question, any doubt here?
No, ma'am, we will have it in the end. We are noting everything.
Okay. So now using that, basis functions, with these basis function, how are we going to represent, our y's now? See, we have this basis function. Okay. So instead of mx plus c, we will now write it in terms of a basis function. Okay, so now this basis function we can write it as y is a function of your fx plus your noise is there, okay, plus epsilon. So this is the case when you have a non-linear relationship between your y and x. Fine. And the same thing, it goes that if you have an IID sample and all those things, so it will be a product, and then it goes, you have this likelihood and all those things. Okay, so you maximize the likelihood with respect to W, what we discussed before, same thing. Now, here, one thing what we assumed is your X is univariate. Suppose if your X is multivariate, then you call that regression as multivariate regression likelihood. Okay, so now look here, if you look here, my X is a multivariate. Okay, now if I consider the Y in terms of this multivariate X, I can write it as this. Now, I'll have a matrix full of this W's for my parameters, my parameters M and C. So I can write it as W transpose Xj plus epsilon. Okay. So now the thing is, how will you write the likelihood function for this multivariate regression problem? It becomes instead of sigma, basically it becomes your covariance. Okay, so I've written it to I'll come to the covariance afterwards. Okay, so for the multivariate regression likelihood, you can express like as what we have done for the univariate regression problem. Same thing applies here, and you can come up with the likelihood function like this for a multivariate problem. Now, for this multivariate problem, this is our likelihood. Okay, so we have to assume, as we said, that we have to assume some prior also. Fine, so we will be assuming, since this is, if you look at this expression, basically this is your Gaussian. Okay, it is a Gaussian multivariate, right? So you can say that you have to assume Gaussian prior. Okay, so we'll be assuming a Gaussian prior here. So you have your prior, you have your likelihood, you try to estimate, you try to update predict your posterior. Fine. So you try using the prior and the likelihood, you try to estimate the posterior. You have different derivations. I have not written the derivation. I didn't want to go to the derivation and all. So you try to update the posterior, and this is what your posterior is. Okay, this is the equation for your posterior. Now, particularly why I have written this in the red is, this is basically your covariance function. Okay, this is basically your covariance function. And this has a lot of importance in the machine learning. Based on the covariance function, you determine, what type of optimization or what type of kernels you are going to define for your machine learning problem. Okay. Now, the same thing, posterior, if I write it, okay, if I write it in terms of Gaussian distribution, I can write it like this. Gaussian distribution, which has a mean, which is characterized by mean, W given mu and C. Okay, so where this is your C is your covariance function, and which also determines your kernel, what you are using for your machine learning application. Okay, and where your mean is your this parameter, and you go on. This is just you try to find out from the posterior. Maybe you can find out this marginal likelihood also, where you can say that your marginal likelihood is characterized by this mu and this sigma. Okay, now this is all about a brief introduction to multivariate regression problem. Now coming to the models, what we were using in the the classification problem, how for the regression problem, what models can you use? Basically, if you look for the models used in the machine learning, basically there are two type of models: parametric models and non-parametric models. Okay, in non-parametric models, they're not priori information is not given to you, but you just try to determine your data. You try to infer your data, get the inference from the data. But in the parametric model, you will be given a priori information, and from the priori information you will try to estimate the posterior. So these are some examples of your models. For the parametric models, your SPM. Okay, and then you have your neural nets and all those are your parametric models. But coming to non-parametric models, your K nearest neighbor, and then you have your Gaussian processes. This in the Gaussian process and in the K nearest neighbor, you're not specified with the priori information, but you try to determine the posterior from the data. Okay, so our main concentration for this talk is the Gaussian processes. This give you to give you a glimpse of how the bivariate. I talked about the multivariate Gaussian distribution. This will be the form of a multivariate Gaussian distribution. Okay, coming to the Gaussian processes now. So basically, Gaussian processes is a generalization. As the name suggests, you have Gaussian distribution associated with this Gaussian processes. It's basically a generalization of many Gaussian distribution to multiple variables. Okay, so you can say that Gaussian process is basically a collection of a random variable, okay, out of which any finite number will have a joint Gaussian distribution. So it's a collection of many random variables where a fixed number will be having, any finite number will be having a Gaussian distribution associated with that random variable. So, and I've already told about the non-parametric method. It's a non-parametric method of modeling the data. So for this Gaussian process, this is always characterized by a mu and a covariance function, which is a positive definite covariance function, where your function, this is your function in the X domain. Suppose if your function is in the X domain, your Gaussian processes is denoted by, suppose if I quantify this, not quantify, if I express this Gaussian processes with a function, okay, which is in the X domain, okay. So this mu will be, mapped from X to real number, and similarly your covariance matrix will be, the product of the X cross X, and that will be mapped to a real number. So your Gaussian processes will be characterized by these two parameters. So now coming to an example of a Gaussian process. So I told you that it's a multivariate Gaussian distributions will be there. So I don't know whether I have, yeah. So this is my multivariate Gaussian distribution. So multivariate Gaussian distribution, I'll have different Gaussian distributions with different mu's and with different sigmas. Okay, so suppose if I have a prior something like this, and so the posterior will be, I can update my posterior according to this. Okay, now if you look at this posterior, this is a common point where all the multivariate Gaussian distributions meet. Fine. So these are your common points. Fine. So in this curve, so these are your predicted values for any function, which is, suppose if this is your function. Okay. If suppose this is your function, this dotted line is your function, and you try to put many multivariate Gaussian distribution on this function. So that is what is happening. Look here, you try to put many Gaussian distribution on any function. Function is given here. And the common point, what you get from this where all the Gaussian distribution coincides, these are your observation points. So this point, I'll come to that. This is your mean, basically, what we discussed in the previous slide. So a Gaussian process will be characterized by the mean. So how much your Gaussian distribution is being distributed in the space with mu mean and with sigma covariance. So suppose if you have a prior something like this, and the posterior will be updated like this, and based on this posterior you try to find out these observation, and then you fit on your curve on this original function. So this is your Gaussian process prior and your posterior. So some of the covariance function, what I discussed in the previous slide, the covariance function can be, these type of covariance function. It can be a squared exponential, Mattern, neural network, and periodic, covariance function. What you generally use in your machine learning. Okay, so I'll clarify this in the coming slides more, how to get these points and all those things. So suppose now you have a space is given to you, a d-dimensional space is a hypercube is given to you, and you have to find out which solution is the best solution that, or which is the global optima. As I told you, you will have minimum optimas, you will have global optimas. So which is the global solution which is there? So usually, in search approaches, you can have your grid search and you can have your random search. In grid search, what you do is you try to distribute your search space into grids, and then you find out in each grid. Okay, so that increases your complexity. And in the random search, what you do is you just randomly search the entire space and then find out, which is the best, like the solution, or which is the best solution. So these are the two general searches what is available. Now, if you consider both these searches, in both the cases, the complexity increases if the function what we discussed previously. Okay, if the function is basically your Lipschitz function, I don't want to get into the Lipschitz function and all. If it is a Lipschitz function, so it varies according to the complexity of that L Lipschitz, you call it as L Lipschitz, so it varies according to L by epsilon. So you have a function for that Lipschitz, and it varies according to that. So that much complexity is there in this grid and random search. To avoid this, the complexity, which I think, I have mentioned here. Okay, to avoid that complexity, what we do is we come up with, some better alternative of search approach using the Gaussian process. Suppose this is your function and you want to find out where is my minimum point in the entire search space. Okay, so this is my optimal value. And if suppose this function is your Lipschitz function, as what I said here, okay, this is the condition for Lipschitz function, fine. And this is basically, you have this, this is your global best point, and this is, the best solution from grid search. So if that is being less than some quantity epsilon, so this is the number of evaluation what you need. So instead of having this much evaluation on this particular search problem or particular minimization problem, we will go for a better alternative using the Gaussian process, and that process is called as the Bayesian optimization problem. Okay, so in the Bayesian, so this is the reason why I went through all the probabilistic approach, so that I can come to the Bayesian optimization right from the machine learning perspective. So we have looked for the optimization, we have looked for the Bayesian approach also. So we'll try to combine the Bayesian approach with the optimization approach in the Bayesian optimization. Okay, so in the Bayesian, what we do is we try to encode a prior distribution over function that explicitly encodes assumption. So now this is your function. Okay, so you have to find out the minimization of this function. Where is the minimum point of this function? So you try to encode a prior distribution over this function. Okay, and then what does optimization do? Optimization use the prior distribution, condition on that function, okay, and determines where to evaluate the next point. I'll discuss it with the examples. Okay. So in Bayesian optimization, basically this is a global optimization. So when I was talking about the conjugate, coordinate descent and all those things, there is one disadvantage about this coordinate, conjugate descent and all those optimization approaches, that they hit at the local optimas. Okay, so instead of finding the local optimas, we go for the global optimas. And so Bayesian optimization is a method of using global optimization. So to find out Bayesian optimization, basically you have two principles. You have this surrogate function and you have this acquisition function. You use two type of functions. So surrogate function means you have a function which has to be minimized. So instead of minimizing that function directly, some surrogate model on that function, and that surrogate model is your Gaussian process. Okay, and the acquisition function will tell you where you have to go and search at the next level. So this is the use of the surrogate function and the acquisition function. So surrogate function make a posterior over unobserved points based on the prior, what Gaussian processes does. So, like you try to, like an example of this surrogate function is your Gaussian process. where you try to use your likelihood to find out the posterior and based on some, prior. And next is your acquisition function. This is a common terminology in, machine learning, exploration and exploitation. So exploration means, I told you about the search space, okay? How much you have to explore. Exploitation is like if a particular area is there, how much, I should exploit that particular area. So there's a trade-off between exploration and exploitation in the entire machine learning. You try to seek points with high variance and you try to seek places where you are already doing well. So you should go for the place where you are already doing well, or you should seek for places where you have a high variance, and you have different acquisition function. I'll not go into this the algo part of it. I'll give you an example of Bayesian optimization that will make the concept more clear. So suppose this is my function, this is my true objective, this is my function fx. Suppose this is my function, this green one is my function, okay? And this is my prior information. Suppose I have a prior information at this point, fine. What I do is, and I try to fit in different multivariate Gaussian distribution over my true objective or over my function fx, okay? So I'll try to fit in many Gaussian distribution over this function, fine, and I'll try to find out a point where they merge. So now suppose I told you about this acquisition function, right? Acquisition function. So what I'll do is, suppose you have different types of acquisition function. I'm not going into that. You have expected improvement, maximum probability, maximum of the probability. Then you have lower confidence bound. You have so many. So so what you do is, if you have an observation, okay, there you don't have to search much, okay, because you have an observation. This is a point like you already got. So wherever you have an observation, your acquisition function will be the minimum, okay? And what you have to do in the Bayesian optimization is, you have to search the space where your acquisition function is maximum. So either you will search in this space or you will search in this space. Okay, so if you consider that you're searching in this space, so what will happen to this curve is, look here now. Suppose you are going to search at, you searched at this point, and this is the point where you are, you are trying to fit in your Gaussian distribution, and this is the point where you got the next your observation, okay? So now when you plotted the acquisition function, this is what your acquisition function is getting. So now look here, what is your current best? It's changing, okay? So current best function is, it's changing, fine. So now you just go on searching the entire space till you get, look here now, so now you get here, okay? So you go on searching your entire space like this till you achieve, something like this sort of function, or maybe, yeah, I think I have something more, yeah. So fitting a Gaussian processes on any function, I can, come up with, the reduction of the complexity in the entire search space for the machine learning. I don't have to search the entire space to find out the optimal values. So these are some examples of the acquisition function, lower confidence bound. I don't want to get into all these things. So you have your MPI, maximum probability of improvement. Then you have your expected improvement. You have many, you can design your own acquisition function. Okay, now this was the theory about the Bayesian optimization, about the Gaussian processes in the machine learning. And it was widely used in, you use neural networks, right? For the hyperparameter tuning, you use Bayesian optimization widely, and this is just an example of, for hyperparameter tuning. So look here now, the complexity, the value where in the learning rate, see how it has reduced a lot. Coming to it is used in the controller design and chemical design and drug discovery and neurology. This is what we have done actually. This is what I have done in collaboration with Ford. And so what we have done is we have to design suspension. Maybe it was an effort towards autonomous vehicle. So we have to design a suspension using the Bayesian optimization. So we have to, what if a suspension is there, where are these these arms located? How am I going to find out where my arms will be located, or where the spring will be located in the entire search space that we have solved using, Bayesian optimization, which we have filed a patent with US and I think Europe. So yeah, for that I just took this, we had a model. Usually, mechanical engineers use a model, Adams, to design all the simulation, multi-dynamic bodies and all, which is your suspension or car, anything, you can design airplane, aircraft, anything you can design using Adam, multi-body simulation tool. So we designed it, we learned how to design a suspension using this tool, and then we tried to automate it using Bayesian optimization. And apart from that, what we have worked on is VFT S352 stars are there, massive stars are there. How are you going to model the parameters of this star? The stellar parameters that we have modeled using the Bayesian optimization. And currently I was working with the stabilization of the rotary inverted pendulum using the Bayesian optimization. So yeah, very soon we'll be submitting a paper to IEEE transactions on cybernetics. So this were few of my works in Bayesian optimization. So yeah, a lot of theory is also put into it, but I've just given you a glimpse of the main concepts of Bayesian optimization. So main reference was this Gaussian book, Gaussian Processes for Machine Learning by Rasmussen and Williams. And if you people are interested in this work, yeah, you can refer for this. You can refer this book, and it's a quite interesting book with a lot of details on machine learning. And yeah, as I work in computer vision, Bayesian optimization, and causal AI. So so that was all about my talk, and thank you for your attention. And yes, I would like to take the queries if
Yes, ma'am. We would like to ask you a few questions that we have noted down. So firstly, what interested you in your current field of work, and could you please tell us about your inspiration?
For the Bayesian optimization?
Yes, ma'am.
The reason is actually what happened is when I came to know about the conjugate gradient methods, and I came to know about, I don't know if you people have heard about genetic algorithms, evolutionary computations and all. I don't know you people have heard about it or not. So evolutionary computations and, your all the derivative optimization methods, they hit at the local minimas. So you don't get a proper global optimas, and you don't hit the proper solution. So that's the reason why I went for these type of derivative free optimization approaches, which is your Bayesian optimization. And a lot of people are working in, you have your Amazon, you have your Uber, you have your Google, you have your DeepMind. A lot of people, Apple, so many separate separate wing is there on Bayesian optimization. I've just given you the basics of Bayesian optimization. So yeah, that inspired me to go for this work. And yeah, okay, it was more of a practical problem which was done in collaboration with an industry. So that is the reason that is also one of the reason why I went for this particularly suspension design. And that stellar parameters, I think one of our collaborator had a project from ESA, European Space Agency. So this was a part of it. So yeah, this was my inspiration.
Okay, ma'am, that indeed is a different story. Ma'am, so another question that we have received is, what is the future scope of image processing and computer vision? How can it change the way we use technology?
Okay, you know where computer vision, how much computer vision has evolved. It started in way back in 1966 from a lab of Marvin Minsky at MIT. And we know where it has gone to in the present scenario. So, and we know what's going to happen next. Computer. If you look at the computer vision, everything is, we know what your AR, VR is happening. AR, VR, and all is AR, VR, and all is computer vision is a main part of AR, VR, and all. So everything is, we are in the pandemic situation. I hope many of us first year classes have not started for you guys, right? So you are at your home, okay? If you are given a virtual environment of your classroom, right? You would be more happy to have your class students, your friends sitting there, so I feel this is a good scope which is coming, which has already started and people are working towards it. And your autonomous driving is a part of it, is a future scope of your computer vision.
Yes, ma'am.
So yeah.
Okay.
Scope is so much. Computer vision scope, it has a lot of scope in in the present scenario.
Yes, ma'am, that's very true. Ma'am, the last question is, what is your message to the current first year and second year students to motivate them to move towards this field of research?
To motivate towards this field of research. I would say that, you are first year students or second year student, try your level best to attain the maximum from any field, be it this field or any field. Try to get the maximum and give your best. Give your best so that tomorrow the society is benefited out of that.
Yes, ma'am. Then, ma'am, there's another question, which is, do Bayesian method have any extra efficiency in real life case, like the one you are working on right now?
If I talk about that Ford problem, engineers used to sit for months to design the suspension, right? We all know, right? Mechanical engineers used to. You forget about suspension. You take any mechanical part, okay? They sit for months and months to design, any multi-body systems, right? So these, like the tools, multi-body tools can help you to design this. And on top of that, if you collaborate, if you merge the optimization approaches with these multi-body tools, that solves out a lot of them for our engineers, for people who are sitting for months to one more application is there, like when the function is very expensive, when the function is very expensive, that time also you can go for Bayesian optimization approaches.
Okay, ma'am. Ma'am, yeah, so that was indeed a very wonderful session and all of us learned quite a few new things. We are really glad to have had you here. Thank you so much for taking out time from your busy schedule and joining us here. I would also like to thank our audience for their active